to get you guys started, let's say that each of these charges is of the same value, Q, okay? And that they're located at 3 of the vertices of a square of side length S. So here, S, and each of these is value. And I'm gonna go ahead and put capital Q today because I want to. And let's say they're all positive. Now, what I'm going to ask you, I believe, is an exercise, and I'm hoping you'll treat it as such. I'm going to bring a 4th charge, and that 4th charge is going to be placed at the vertices in the bottom left-hand corner, and it is of charge Q, but I'm using the lowercase q to describe its charge. With what you've learned so far, could you come up with the size and the direction of the force on the red charge? Do you think you have the capabilities to do that question? And I'm interested in seeing it. So why don't you talk to the folks around you and see if you can come up with a way to get to the answer. So again, I have a square of charge. The square has side lengths S. The 3 white charges are positive capital Q, and the red charge is positive lowercase q. And I would like the force on the red charge. I am going to give you a couple of hints. Your answer is going to have probably capital Q, lowercase q, S, and K in it. All right, that's probably all that's going to be allowed in our answer. And when I say direction, let's go ahead and say that this is the positive y direction, and this is the positive x direction. Okay? Now remember, force is a vector quantity. It has direction. So expressing the direction is something separate from expressing the magnitude of the force. All right, give it a try. See what you can kind of bang up and come up with. In doing this question, I think we can all agree that these two charges and these 2 charges will be applying the same size force to the red charge, right? Same 2 charges, same separation distance. But the direction of that force is not complementary to the 2 of them, right? They're at a right angle to each other. So there'll be a force this direction from those 2 charges and this direction from those 2 charges. You're going to have to deal with the fact that they're not in the same direction. They're in a 2D field. Now there's a third force that exists between these 2. Different separation distance, so you're going to have to deal with probably figuring out what that separation distance is. But that's going to produce a force that's like this way, right? So not only do you have to figure out the size of these forces, but you're going to have to deal with the fact that they're not all in the same direction. So there's some trig here and some geometry here. It's all that's been introduced. There's nothing really new added to last week, but you will have to deal with the geometry of the problem. That's probably your biggest weakness. So think about the geometry and how you're going to resolve it. Most of you have reached a point where you've come up with the value of the size of all the forces. So you know that the force in this direction is QQK over S squared. And you know that the force in this direction is the same, QQK over S squared. Is there any question where I got either of those from? Because I didn't see it on everybody's paper, but I saw it on most. And by paper, I mean whatever the heck you're writing on. There is this distance. And let's all be realistic here. Some of you know it's square root of 2s, and some of you don't. It's worth it to remember some of your basic geometry here, right? You could use the Pythagorean theorem to figure out that it's a square root of 2 times s, but it's probably going to be in your best interest to have certain things like this memorized. A square is going to show up probably on the exam. Let's know some square things. Is that okay? So square root of 2 times s saves us some time. And that means this force, which is probably less than the others, QQK over 2S squared. Are we good? All right. We can't just add these three up, right? Because this force and this force are not pointed in the same direction. We have to find the component of those forces along our resultant direction. But again, I don't want to make this hard. I know that this is the resultant direction, don't you? Yeah. So since we know that, I just need to multiply this by like sine or cosine of 45 degrees, since they're the same. But that's just 1 over the root of 2. So that's what I'm going to do. I'm going to say the part of this force that's in this direction. Right? Draw myself a little picture there so that those of you who need a visual representation, note that this is going to be 45 degrees. And based on the way I've drawn this, I'm looking at the cosine of 45 degrees as the component I'm interested in. But that's just going to take this and be multiplying by 1 over the root of 2. Right? Or you guys probably would think square root of 2 over 2, because that's how you guys did it in your class. Right? All that unit circle work, this kind of came up a lot, didn't it? Or at least a couple times. That, the 30, 60, 90, and the 45s. So you know all those. And I can probably put that right here too, that the only part of this I'm interested in is that part of it. Are we all good? Add them all up, got our answer? Do you see why this is like a multiple choice question? There's really not that much work here. You could probably recognize it from a list of answers. But I want to finish it out. So we'll have QQK over root of 2 S squared. And there are 2 of these. Plus QQK over 2 S squared. This is the magnitude of our answer. Now, we can do some work here, some mathematical work that I think is probably in our best interest. So I will pull out the QQK over S squared, since it's common to both. And then we'll just have a factor in here. 2 times 1 over the square root of 2, 1 over the square root of 2 is just the square root of 2. Plus 1/2. I think we're done. Any questions? Are we sure? Did I go fast enough or slow enough? Don't know which is which. Gladys, you okay?
Can you just reiterate where you got the 1 over square root of 2?
Sure. I have it memorized. I thought you guys did from the unit circle. So if you don't, it's okay. It's from sine of 45 degrees or cosine of 45 degrees, right? Which is, I don't know, pi something or others. Don't really care. But if you do math on it, it ends up just being 1 over the root of 2. Is that okay?
Yeah.
Okay. Anybody else? Okay. These kind of geometric problems show up a lot, usually based on relatively straightforward shapes. Squares are common. Now again, this problem becomes way more difficult the moment the charges are not in a symmetrical pattern like they are here. But don't be fooled. There are simple ways to tweak this question but still exploit symmetry. Like if this charge isn't positive but is negative, right? It makes its component in the opposite direction. I'm probably just going to put a negative sign in here somewhere, but it's one of those things where they're still looking to maintain a certain amount of symmetry. And so a lot of times, just to make sure you understand the vector portion, but without making it a difficult vector question, we'll have problems like this. So expect like squares, equilateral triangles, and even things like standard isosceles triangles, where you have 2 common angles that are the same. They make for a relatively straightforward question with exploitable symmetry. Follow along so far? I want to talk about some other problems that have similar exploitable symmetry, okay? This next one is going to increase the level of difficulty, but only by a small amount. Is that okay with all of you? Working out a portion of one of your homework questions, the last one. And there's two that are like this. One is directly off of an old AP exam. The other one is one that I wrote, so it stays within this particular unit. Again, these questions wouldn't be what they're like on the AP exam, especially today's AP exam, but they are reminiscent. They don't ask much about forces, they ask more about fields. So I'm going to draw a few things in here. Assume that this vertical line represents, I don't know, for you guys, we'll stick with something that's in your wheelhouse. We'll say this is the x direction. And the origin of this line is, say, here, and we'll say that's 0, okay? Now, I'm going to place a small positive charge here, maybe not, let's try that again, here, and a duplicate positive charge, maybe not, here. And I'm trying to make sure they look equidistant from the axis. Do they look equidistant from the axis? I'm going to draw a line in here. This line is just to help us and for me to make sure that I've lined everything up appropriately. So, all right, so let's, here we go. All right, let's call this distance A. Let's say that I have charge Q and charge Q. Somewhere on this x-axis, I'm going to place another charge. And we'll say it's negative Q, just for funsies. The problem isn't any different if I put a positive Q there. You probably understand that, right? And this charge is a distance x away from the origin. I'd like the force on the red charge in terms of the variables given and any fundamental constants that you'll need. For us, the only fundamental constant we've talked about is K. This is a more challenging question, but has exploitable symmetry. Now, I want you to think for just a moment about the scope of your answer. I'm not asking for an exact answer. I'm asking for an expression. And I'm probably interested in talking about how variables like A and X affect the answer. For example, can you all agree with me that when X is 0, the red charge will be at the origin and will experience a net force of 0? We saw problems like that last week. I also expect that as X gets bigger, the force is probably going to get smaller because it's getting further away. So I know I have to have an equation that does that. My answer must have a look about it, that when X is 0, the force will be 0, but when X gets big, the force goes to 0 again. Can you set this problem up? This one's a little bit harder to set up, and I'm willing to give you a hint, but I want to wait to give the hint until some people have gone off and started running. So why don't you start? I would focus on pairing up one of the white charges with the red charge and consider what it would look like. Let's talk about hint number 1. I didn't give you the separation distance between the charges, right? Between the red charge and the white charge, that was not given. You'll have to infer it with the information that has been provided. Right, if we talk about Coulomb's law is about the separation distance. Well, that separation distance is from here to here, correct? You will need a way of expressing that only in the variables provided. Okay, that's a hint, pretty big one and pretty obvious one. But you'll have to use something that uses X and A, but doesn't use, well, in this case, R right? Because that's what this is. This would be the value for R in Coulomb's law. Let's talk about what that probably looks like then, shall we? Did you come up with at least one of your forces, which is going to be negative Q, Q, K over, not R squared, but the square root of A squared plus X squared squared. And I know I've left I don't need to have the radical there. I'm just trying to make sure that everybody's kind of on the same place as I am right now with this. That good? Any question about where I came up with any of that? Let's talk about symmetry again. This force is in this direction. Do we see the symmetry in this problem? So do you recognize that there's going to be an equal sized force on the other side of the x-axis that's going to point in a similar direction? So we only want a portion of this force. We want the part of this force that is along this line. I'm thinking cosine, right? Cosine of whatever this angle happens to be, theta. Right? In fact, my expectation is that I only want the part of the force in the x direction, which would be this force times the cosine of theta. Do you understand what I've done? I'm not looking at the y component of it. I want the x component. And there are two of them. One from the top, one from the bottom. Theta can't be in your answer. Theta can't be in your answer. Find a way to write theta without writing it in terms of theta. Not trying to leave anybody out. So my goal here is to actually go pretty slow with this kind of stuff. Just putting this triangle on the board. Is that okay? You guys see this triangle here? Yes. And this triangle has properties that include theta, right? And side lengths that we have figured out. For example, we have figured out that r is the root of a squared plus x squared. And the adjacent side here is x, and the opposite side is a. We don't actually need theta. We need the cosine of theta, right? Although I said we can't have theta, find an expression for theta, you don't really need to do that. You need to find something to replace the cosine of theta. Well, the cosine of theta is defined by the sides. Adjacent over hypotenuse. So cosine of theta is x over the square root of a squared plus x squared. That's the cosine of theta.
So simple.
It's not simple. I'm sorry, this is hard. When we talk about why this class is hard, it's not necessarily because the rule, Coulomb's law, is hard. It's hard because you have to think differently about the way you've been taught geometry and the way you've been taught trig. So do we understand where this is coming from now? Where I'm going to get my cosine of theta has nothing to do with the angle really anymore. It has to do with the terms of the triangle that we created to solve the problem. There is no r in this problem. We found r by looking at the triangle that was implied. All okay so far? Bring all the pieces together. You'll hear me say this a lot because there's a lot of pieces moving around here. So I want the net force, which is only going to be the force in the x direction. So I'll put the x here as a reminder that I'm only looking at the components of the force in the x direction, because the components of the force in the y direction cancel out. So they're gone. And that's going to be, there's a bunch of stuff here, but I'm replacing this where I see cosine. Right? There's a 2 up there, so I know I need to keep that 2 in mind. So I'll have negative 2QQK. And I'm going to combine things the way I want to see them. So I'm going to put over here x over a squared plus x squared to the 3/2. Because I had a squared plus x squared, and I'm multiplying by a squared plus x squared to the 1/2 power. That gives me the 3/2. And that's the answer. That's the net force on the charge. It's got all the components in it that we're looking for. Now let's see if it does what we said it's supposed to do. Because we said, for this to work correctly, the force has to be 0 when x is 0. Will it be? When I put in a 0 for x, does this function go to 0? It does, because the top will be 0 and the bottom will be a cubed. All good? Does it go to 0 as x goes to infinity? Now, you guys did limits if you were in calculus, so you understand limits. Kind of a funny thing. The top's going to be x going to infinity, but the bottom is going to be x to the 3/2 going to infinity. So the bottom is going to get bigger faster than the top, so yes, this will descend to 0. In fact, it descends to 1/x squared, which then goes to 0. First time seeing this is not easy. There's a lot of parts here. And you're going to hear me say this a lot. It's not the physics that's often hard. It's the geometry. You have to find a way to wrap your head around the geometry you've been given. This is the geometry we were given. So, in the spirit of wanting to make sure you guys are growing as we do this, I'm going to make a minor change to the question, not help you at all, and I want to see you work all the way to a solution. Okay? The minor change is this. In the new version of the question, this charge is negative. Okay? Come up with an expression for the net force on the red charge.